So in the last lecture, we looked at the steps for designing a fuzzy controller, and we also solved one problem of a fuzzy controller for a washing machine. So quickly, just let us revise the steps that are required while designing a fuzzy controller. Okay. So what is step one? What is the first step?
Identify input output.
Inputs and outputs, right? And also decide the descriptors for the input and output functions. Next step. Once you identify the inputs and outputs and the descriptors for the same, what do you do? Yes,
Design membership.
you define the membership functions, right? You need to form fuzzy sets out of these, right? So you define the membership functions, define the MFs for all the inputs and outputs. Once your MFs are ready, what is the next step? We're done with everything representing of inputs and outputs. As far as that is concerned, we are done. But what is the heart of the system?
Form a rule base.
Correct. So you need to form the rule base. So you decide what will be the rules for inference. Okay. Next, what you will do is once your rule base is ready, you will check whether for a given set of inputs, what you are getting as output, right? So you will test your inference mechanism. So what is that? That is nothing but rule evaluation. So whatever type of inference system that you have. So which system we were talking about, whatever we did there, what did we use? We made use of what is known as the Mamdani fuzzy inference system. Different scientists have proposed different ways of inferencing. Okay, so one such is Mamdani fuzzy inference system. So we use that. What is uh, specific about this is the defuzzification technique actually used is mean of maxima. Okay, I will talk more in detail about this system. What are the characteristics in a later lecture? I will definitely talk about this. But this is what we used. We used the Mamdani fuzzy inference system where mean of maxima is used. And do you recollect how did we evaluate the rules? Which operator we used? So you had the if then rules. Yes. So we had the if then rules. In the if part, we had two input variables for the machine, washing machine, dirt and grease. So we all our rules that we had written in as part of the rule base, they had which operator? They had the and to combine the two facts. We use and operator. So for that, made use of main operation. Okay. So that was about rule evaluation. So when you are evaluating the rule, you are starting from all representing all these facts, which you're finding out actually which of the rules are firing for a given input value or a given set of input values, which of the rules in your rule base are actually firing and to what extent they are firing. That is what you do as part of the rule evaluation. Apart from that, what do you do? At the end, once your rule evaluation is done, what is the output of the rule evaluation? The output of the rule evaluation is it a crisp value? What is the output of rule evaluation? Is it a crisp value? You are getting some fuzzy values, right? You're getting some fuzzy values. Output of rule evaluation is a fuzzy set. Output is a fuzzy set. You're getting fuzzy values. Okay. Using those values, you need to find out what is a crisp value corresponding to that final fuzzy value that we have got. So for that, we are using defuzzification. Output of rule evaluation is a fuzzy set. So you need to look at that overall output fuzzy set. And for that output fuzzy set, you apply the defuzzification method. And the method in this case that we have used is mean of max. Okay. So these are the steps. Finally, when you apply defuzzification, you will get the output, the crisp output. So when you perform all these steps, you go from input to output. That entire FKBS that we saw, the fuzzy knowledge based system, okay, is actually nothing but these set of steps. Okay. So with this recap, let us move ahead with one more problem which we'll solve today. Okay. That is this one. So you have to design a fuzzy controller for a train which is approaching a station. What are the inputs? Inputs are given. They are distance from a station and speed of the train. So this is a somewhat tricky problem, I can say, because you have to think here very carefully while designing the rule base. Okay, that is why I've taken up this problem. Okay, so design a fuzzy controller for train approaching a station. Inputs are distance from a station and speed of the train. So two inputs are given to you, speed and distance, and the output is brake power that you need to compute. So some guidelines are given as far as the system is concerned. You have to use triangular membership functions, four descriptors for each of the variables. 5 to 6 rules are there, but we will write all the rules which are there as part of the grid that we have, okay, or the matrix that we have. All combinations we'll write and use the appropriate defuzzification method. We are using Mamdani only here, so we will go for mean of max. Okay. So for this particular example, again you will have to start with all the steps one by one. So let us solve. Okay. So the distance, speed, and brake power. You have to you have already given, they have already given, you just have to write the descriptors and the ranges for each of these input and output variables. So what are the what will be the descriptors? They have mentioned in the problem statement that you have to use 4 descriptors for all the variables, right? That is given very clearly. Only thing is you have to decide the range, okay, range of values. So what we can do is you have to write your assumptions. Whatever assumptions you're making, you have to write. So if you're saying that this is the range of distance, you just say this is the range of distance. Don't just draw the graph directly. Here at this step only, you have to make the assumptions. Okay. So since there are 4 descriptors for each variable, so the descriptors for distance could be very short distance left. So basically what you have to do is the train is approaching the station and the brake has to be applied. So what is the brake power that is required so that it halts, right? That is the problem that we are trying to solve. So given that this is the distance left and this is the speed of the train, what is the brake power that is needed so that it stops at the station? That is what we are trying to solve. Okay. So the distance is very short distance. Okay. That is writing the descriptors. Short distance, long distance, very long distance. Okay. So let us assume that we decide to apply the brake maximum at say about 500 meters. So this could be the range 0 to 500 meters. From the station, the train is away. 0 to 500 meters is the range that we're looking at. And speed, speed of the train. Again, there are 4 descriptors that you need to write. So what will be the speed? Again, very low speed, right? Low speed, then high speed, very high speed. Okay. And the speed, again, you have to specify the range. I'm just assuming it is 0 to 60 kilometers per hour. Okay. And the brake power, again, very low, low power, high power, very high power, right? And let us assume that it is in terms of percentage. You can write it in terms of horsepower and whatever the unit, whatever is the unit of power, or I'm writing it in terms of percentage. Okay. Whatever is your assumption, it could be percentage, it could be the unit. You write it. That's it. It's not hard and fast that it has to be in this unit or that unit, but whatever is your assumption, write it. Okay. Because we are not domain experts. That is the underlying assumption. We are not domain experts, right? So, but only logically, whatever your design is, that has to be correct. So, as per whatever we have written, as far as the speed is concerned, let us define the membership functions for speed, distance, and brake power one by one. So, speed, every remember every input and output is having 4 descriptors each, right? So, for you'll have to break it up into 4 functions. So, let us first plot it. Okay. So you can assume different ranges. I'm assuming. So see, what you will do is I'm making the design for you right now. So I want you to solve it. So when we write the functions, I mean, when we are doing the rule evaluation, at that time, whatever inputs I'm mentioning, for those inputs, you should get the same answer. So that is why you are following this. Otherwise, you can choose your points here, right, on the scale. Now you're going to solve it along with me. So 0 to 10, say, then 10 to 50, 50, and then 50 to 60. We have assumed 60, right? This is somewhat uneven. It's okay. I'll just try to draw it to scale. 0 to 10, 50, and then 60. Okay. So let us assume the variables as x, y, and z like we did for the washing machine. So this is x. This is mu of x. Okay. So first one is what are the descriptors that we have used? Very low speed, high speed, and very high speed. So first one is very low speed. What kind of function will it be?
Decreasing.
Decreasing function, right? So very low speed. Then it is very high, low speed. Low speed. So now it is up to you where you want this, but whatever I have solved, according to that, I'm doing it so that when you are solving for rule evaluation, you get the same answer. So it is not necessary that this is having symmetry, right? So 10 to 50, 0 to 10, 10 to 50, something like that. That is what I'm doing here. You can have this point here also, somewhere in between at 20 or 30, whatever. Okay, that is up to you, your design. Next is high speed. So this is where this is low speed, right? Then is high speed. Again, high speed, you are saying, again, you can start from here, but right, high speed. So this is what, and sorry, yeah, this is high speed, and finally you have very high speed. Okay, so high speed and very high speed. So you by now you should be well versed with writing the functions for the variables. Okay, so for speed, again there are four different functions. So mu of x is nothing but that is what is the first function? Increasing function, sorry, decreasing function. So that is 10 minus x divided by 10, right? So from 0 to 10. I'm not writing x here, but it has to be 0 less than x less than 10. Okay. Then next is low speed. Low speed is divided into two parts. So one is between 0 to 10, and next is between 10 to 50. Okay. So low speed is first is increasing function. So what is it? What is the function? By now you should be well versed with writing this. What is the function equation of this line? X by
Right.
x by 10. Okay. Next is 50. Next is a decreasing function. So that is 50 minus x by what is the denominator? 50 minus x of this line, equation of this line. What is it? 50 minus
40.
x divided by 40. Okay. And so these are the two functions. Next is high speed. It is high speed. Again, increasing, decreasing, it is triangular. So x minus 10 divided by 50 minus 10, that is 40. For the range 10 to 50, and for the range 50 to 60, it is a decreasing function. So it will be 60 minus x divided by 10, right? And finally, very high speed. Okay. Very high speed will be, what will it be? In 50 to 60, it's increasing function. So it is x minus 50 divided by 10. Okay, so these are the functions for speed, right? Similarly, functions we'll define for distance and brake power. So for distance we have assumed 0 to 500 meters. Okay, so again there are four functions. So 100, 400, and 500. Okay. Next is This is y, right? Next variable y. This is mu of y. So again, the same kind of functions we'll draw for distance. Right? So what were the descriptors we had used? Short distance, very short distance, short distance. Okay. So very short distance, long distance, very long. Okay. Similarly, you write the functions for distance. So we'll write the functions so it becomes easy for us to evaluate the rule. So quickly we'll write down the functions. So very short distance of y. What is it? Okay, decreasing function 100 minus y divided by 100. Range is 0 to 100. Next is short distance of y divided into two functions. One is a increasing function, that is y minus y divided by 100, right? Y minus 0 divided by 100. Then second is decreasing, that is 400 minus y divided by 400 minus 100, that is 300. The range is 100 to 400. Next is long distance, again divided into two functions. One is y minus 100. It's an increasing function, this one. So y minus 100 divided by 300, range is 100 to 400. And finally, 400 to 500 is decreasing function, that is 500 minus y divided by 100. Similarly, last one is increasing function, that is y minus 400 divided by 100. So these are the functions for distance. Similarly, we have to define the functions for break power. Okay. So what is break power? Again, four functions are there similar to that only. So let us assume the ranges. We had assumed 0 to 100 as the range percent in terms of percentage. So break power again. So this is 20, 20, and then we have 80 and 100. Right? So this is our z variable. This is mu of z. Again, four functions. Right? So this is what are the break powers that we had decided. Very low power, high power, very high power. Okay. And you define here, so very low power of z. So we will write 20 minus Z, right? 20 minus Z divided by 20. Range is 0 to 20. Next is low power. So from two ranges, 0 to 20 and 20 to 80. So for low power, it is first is increasing. So it is Z divided by 20. And next one is 80 minus Z divided by 60. Next one, high power. What is high power? Again, two functions, 20 to 80, 80 to 100. So 20 to 80, we have increasing function, that is Z minus 20 divided by 60. And 80 to 100, we have which one? 100, 80 to 100, decreasing. 100 minus Z divided by 80. And finally, very high power is
मैम
nothing
वो
but,
पिछला वाला डिवाइड बाय 20 होगा ना?
yes, this is 20, right? And this finally is Z minus 80 divided by 20. Right? So these are the equations. Now we'll move on to the rule base. So speed and distance written on the rows and columns. We have to put in these into the table. So let us say we are writing, thinking of the first cell, that is very low speed and very short distance, right? Very low speed and very short distance. So that means the train is approaching with a very low speed and the distance is also very short. So what should be the brake power? Should it be very low brake power? Should it be very high or high? Can you think? Speed is very low. Speed is very low. Distance is very short. Yes, think. Should I apply brakes with a very high power or with a very low power or low power or high power? You have four options. Very low power is ruled out. Yes. Speed is very low and the distance also is very short. So can I apply a very low power brake?
Yes.
Distance is very short.
No, no.
Distance, you look at the distance. Train is just very close.
Either low power or high power.
Either low power or high power. Yes. Harsh,
Okay, ma'am. Yeah, got it.
got it? Yeah.
Yes, ma'am.
So this rule base actually you have to design carefully. That is why I've taken this problem. So very low speed and short distance. Speed is still very low, but distance has increased. Distance has increased.
Low power.
You are far away na, from the
Low power.
stations, so you don't require. Exactly. So low power. Next, very low speed and long distance.
Very low power.
Very low. And very low speed and very long distance. It's far away, very far away.
Very low power.
Next is low speed and very short distance. Speed is comparatively faster than the previous one. Comparatively increased. Okay.
Low power.
Yeah. So low again. This could be low or high.
Yes.
Okay. Next is low speed, short distance. Distance has now increased.
Low.
Low. Then low speed, long distance. Again, this could be low or high, low or very low, low or very low, right? And this will be very low. Next, clear na? This is clear na?
Yes.
Next is high speed and very short distance.
High
High.
power.
High power or very high power. Okay. High speed and short distance. Speed is increased. Distance is
High power.
also, yeah. So if you take this as very high power, this will be lesser. We'll look at these where we have put a slash, that we'll have to keep only one. Okay. So high speed and low distance. Long distance. High speed and long distance.
High power or low power.
And then high speed, very long distance will be low
Low
power.
power.
Okay. Next is very high speed. Speed is maximum possible. Okay. But
Very high
distance
power.
is very short. Yes. So definitely very high power. Okay. Again, very high speed. Distance is also short. It could be
Both
very
VHP and HP.
correct. And then what you are going to do, of course, very high speed. Distance is also there, considerably large. So what you will do,
High power.
you will keep on decreasing it. Okay. And then this will be low power. Okay. You're getting it. So if you get this kind of a problem scenario, so you have to be careful, okay, while designing the rule base. See, wherever I have put a slash, you can use either of the two, but just try to balance the table in such a way that you have now, since there are four descriptors everywhere, so roughly you should have something, four descriptors of the output, sorry, four descriptors of the output. So you have to have a balance. Okay. So here I can do something like, I can keep this as very high power and this, that is up to you. Either way, one person could put, like for example, in this last cell, this is very high power. So I can, some person could put this as very high power. Some other person could put this as high power. It is fine. There's no issue. Okay. But see to it that everything is covered, like 2323 are there, because there are 16 cells. Okay. So here what you're going to do is, if I keep this as low power, okay, then this I'm keeping as high power, I can do that. But then there's too much of low power, ऐसे नहीं होना चाहिए, because see there is low power everywhere, here. Okay, so you balance it out. So what I'm doing here is high power I'm keeping in the first cell. I'm just removing. Okay, here. Okay, you could keep the other thing, it is okay, no issues. Low power. This is what I have chosen for now. So using this, now we can evaluate the rules. Okay, now let us take some example, and I want all of you, this is the rule base that I have kept. It could be slightly different for you, that is fine, but the equations will be same. Okay, so 110 and 52. If you use this, you will get the same answer that I will get, that I am expecting, if you use this as the rule base. So for now, you can use, please use this as the rule base that is written. Although if it is different, you will be getting different answers, because suppose here whatever the area of interest is, suppose this is the area of interest where the rules are having some strength, then in that case if the function changes, the values also will slightly change. Okay, so now for distance is 110 meters and speed is 52 kilometers per hour, we have to evaluate the rules. Okay, so first of all, we have to see distance is 110 meters is present in which area, so which region, so which membership function is getting applicable for distance is equal to 110 meters. Okay, let us go back to the membership functions. Distance 110, right? 110, that is this region. Okay, so it has two functions, one is short distance and one is long distance. Two functions are there. Okay, so that these functions you have to use, and you have to find out the membership, right? So when distance is 110, which function from short distance you're going to use? This one? Yes or no? And for long distance, you're going to use this one, right? So is this clear? Use these two functions, find the membership value for distance. Okay, so I'll go back to it. I'll write the functions for you. So it is corresponding to short distance. Okay, short distance, I assume this is y, this is x, whatever. Yeah, so that is nothing but short distance function I'm writing here for you. 400 minus y divided by 300. And the other is long distance. Long distance was y minus 100 divided by 300. Okay. So short distance, you tell me what is the membership value for short distance? What is mu SD of 110? Yes, what is mu SD of 110?
0.967.
0.967. Okay. And what is it for long distance?
0.334.
0.334 or is 110
Point
mi-
zero, point zero.
0.033. Harsh, 0.033. It is 10
Ah,
by
300. Okay, sir.
एक decimal. Okay. Next is for speed. Again, which you have to see in which region is 52 lies, right? So we'll go back and check speed graph. 52 is in this range. Okay. So 52, you have high speed and very high speed. So for high speed, you have this function, and very high speed, you have this function, right? So for we'll write the equations. I'll write the equations for you there. Tell me the answers. So high speed is 60 minus x divided by 10, and very high speed is x minus 50 divided by 10. Okay, these are the equations. Now we will substitute the value of speed as 52 in this each of these equations and find the membership. Okay, so high speed of 52 is 8 by 10, which is nothing but 0.8. What about very high speed? 0.2. Okay, now you have got these four values. What is the next step? What do you need to do with these four values? Short, so you need to find the region of interest that you're going to look at, right? Which is the region that I'm going to look at on my entire output curve. So that what I need to do is the combination. So short distance and high speed, right? So all there are four combinations that you will get. So what are those four combinations? Which short, this one, sorry, uh, long distance, and you have short distances. Long distance and high speed. This one. Okay. Long distance with, sorry, short distance with very high speed. This one. Then long distance with high speed. Right? Long distance with high speed. What is it? This one. And long distance with very high speed. This one. So rest all is, we don't care about it. Put across everywhere. So what will come in the intersection of these? These are rules. What do other rules look like? We have used and because we have said that when the distance is short and the speed is high, then the brake power is so and so. So we have used and. So we need to take the min of the values again in this case as well. So min of the values. So which values? The intersection. So high speed and short distance. Look at high speed and short distance, the mean of the values, right? I'll just write for this one block 0.9 and 0.8. That is 0.8 for your reference. right? Next is again high speed and large long distance. What is the value that is expected in this? Can someone tell me?
0.033.
0.033. Next,
Point 2.
very high speed and
Point 2.
point 2, and this is
0.033.
correct. So these are the values that we have got. Now what is the next step?
Maximum.
Yes. So maximum for defuzzification you require. Okay. We finish that rule evaluation there only. We don't require this. So we need to find out the max of these values. So max of 0.8 we had 0.2, 0.033 and 0.033 is nothing but 0.8. So we are interested in this value. That means this rule is firing. Okay, this rule, we have to look at the output of this rule. So what is the output of this rule? Let us go back to the rule base. It is
High power.
high power. So you need to look at high power membership function, high power membership function, and equate 0.8 with each of these, right? You recollect 0.8 with each of these. Okay. So 0.8, those equations, I'll just write down the equations. The high power equation of Z. Z is the variable. High power equations, okay. High power equations are Z minus these two. Z minus 20 by 60, 100 minus Z by 20. Hundred minus Z by. So equate each of these to 0.8. This is equal to 0.8. This is first equation. Second equation. This is equal to 0.8. And find the value of Z in each case. What is Z1? That these actually Z1 and Z2 that you're going to find, these will be the, so that function is there, but it is clipped off if you remember. These will be the endpoints. This will be Z1 on the Z axis, whatever. This is 0.8 and this is 0.8. Mean of max you're applying. This is Z1, Z2. Take the mean of that, you will get Z star, right? Z star. So Z1, what are you getting? Solve this equation. Tell me the value of Z1. Six eights are 48.
68.
68. And Z2, 84. Right. So Z star by mean of max is equal to average of these two values. And what do you get? 76. Okay. So this is one more example, just difference was rule based. So remember all problems, it is easy to solve. but the challenge is the rule base. So you have to understand the problem properly and then design the rule base. Once your rule base is ready, if you're following the steps and you get used to solving those equations and just substituting the values, I think it's very easy to solve the problem. Okay. This is one problem for practice because this is similar to the problems that we have solved. In the next lecture, what we will do is we will solve different problems which involve different types of rules and different types of functions. So one each of both. That is the trapezoid function and the or connective for the rule. Okay. This problem, you please try solving it. If there are any doubts, we can take it up. Okay, please try solving this. It's very similar.